Have you ever wondered what happens when arbitrary numbers are combined? Does it create even more chaos than the individual numbers? Or does the randomness stay the same? Consider the consequences of merging numbers together and the potential impact it can have on chaos theory. Before exploring this question, let's gain insight into the concept of random numbers and their counterparts, which are precise numbers devoid of randomness. Consider the subsequent illustration. What is 3 times 5? Now let's think about this 15. Was it purely a random choice? Is there no particular reason for it? Perhaps could it possibly be 16 rather than 15? Of course not, because 15 is the result of a calculation. There's a logic behind this number that forces it to be 15. We know where it came from and why. We know exactly what sequence of steps needs to be carried out to get that number, which in this case is adding 5 plus 5 plus 5. This makes it predictable and reproducible. We can repeat this count as many times as we like, and the result will always be 15. And that's why it's not random, because that 15 is just a consequence of a previous cause. Based on this idea, and knowing that a random number is the opposite of an exact number, we can conclude that a random number is a number that has no cause. It is not the result of any operation. We don't know where it came from, let alone why. In fact, there's no way of knowing, because there's no logic behind a random number. And it's precisely for this reason that a random number is impossible to manipulate or reproduce, because there is no sequence of steps you can take to get it, and if there were, it would stop being random instantly. A random number is literally a number that came out of nowhere and for no reason. Notice then that randomness has nothing to do with the numbers themselves, but rather with how you got them. And if that sounds bizarre, welcome to our programmed universe. Classic computers, like the one you're using right now to watch this video, are extremely accurate. They are just machines that follow orders defined by those who created them and those who programmed them. Then the question arises, how is it possible for such a computer to generate a random number? Exactly. It's not possible. Classical computers are incapable of generating truly random numbers, as they are always obeying some instruction, whether imposed in the hardware or programmed in the software. The numbers they generate are always the consequence of some previous operation. These numbers have a very well-defined logical sequence, and this makes them reproducible and therefore non-random numbers. There is hardware that specializes in generating truly random numbers. They use some attribute of a real physical system to generate these numbers. The idea is to take advantage of the true randomness of quantum mechanics. But we'll leave that for another video. The random numbers that classical computers can generate are called pseudo-random numbers. They are pseudo precisely because they are not completely random, but they are almost. As the poet would say, 99% random is unpredictable, but that 1% is reproducible. And yes, the randomness in these algorithms is something that can be measured and increased. A pseudo-random number generator algorithm is considered strong when the sequence of random numbers it generates satisfies 2 basic but very important characteristics. The first is that it must take a long time for the numbers to start repeating, and the second is that each number must be as independent of the previous ones as possible. For example, imagine that we drew 100 random numbers using these 2 algorithms. Algorithm A generated this sequence, and algorithm B generated this one. Algorithm A started repeating the numbers as early as the 6th element, i.e., it can only generate 5 random numbers. Algorithm B only starts repeating the numbers when it reaches the 21st element, so it can generate 20 random numbers. Point for algorithm B. The 5 numbers that algorithm A generated are highly related. The pattern is clear. It's always the previous number plus 1. Algorithm B's numbers are much more independent. Point for algorithm B again. In conclusion, algorithm B is much stronger than algorithm A. That was a very drastic example. In practice, it's not that simple, but you get the idea. An algorithm that is often used because it is very strong in these two respects is the Mersenne twister. It manages to generate an incredible 2 to the power of 19,937 minus 1 before it starts repeating. 2 to the 19,000, bro. That's a lot more than the number of atoms in the universe, but a lot more. Just to give you an idea, if you had a computer capable of generating 1 trillion random numbers per second, that's how many years it would take you to exhaust all the random numbers that this algorithm generates. And if we think in terms of energy, it gets even more bizarre, because this number is so absurdly large that most likely, if you took the entire universe and turned it into electricity for your computer, you wouldn't have enough energy to draw all the numbers that this algorithm generates. In other words, it is literally impossible to exhaust this sequence. Although these numbers are not truly random, they are random enough to meet human needs. And that's good enough. And now we come back to the question, what happens if we add two random numbers together? Could it be that the randomness adds up and the result is even more random? What if we add millions of random numbers? Do we invoke the god of randomness in its most perfect form? The answer is really very interesting, and I'd like you to leave your guess here in the comments because I'm going to count each one of them to find out which option won. Hey! What is it, Sarah? You're not going to count them one by one, are you? Okay. I'd like you to leave your guess here in the comments because Sarah's going to count each one to find out which option won. That's it. That's much better. Thanks. So here we go. Adding two or more random numbers makes option A, randomness increases. Option B, randomness decreases. Or option C, nothing. The randomness remains the same. Bets placed? Let's get on with it. To answer this question, here's what we're going to do. Let's create 20 bars, ranging from 0 to 19. We're going to draw a random number that also goes from 0 to 19. Now we go to the bar of the number drawn and increase its size by 1. Now just repeat this several times. First, let's reset the size of the bars. And let the games begin. That's good, that's it. Two things are important to note here. Firstly, since all 20 numbers have the same chance of being drawn, all the bars grow at roughly the same rate. You can clearly see that the pattern here is a straight line. This is called a uniform distribution. It's a distribution because the size of the bar is spread out over several bars, not concentrated in just one. And it's uniform because all the bars are proportionally the same size and always will be. No matter how long I sit here drawing numbers, all the bars will grow at roughly the same rate. And secondly, even if all the numbers have exactly the same chance of coming up, it's still a random draw. There's no guarantee that all the numbers will come out exactly the same. In fact, it's almost impossible for that to happen. So this fluctuation emerges. Some numbers appear a little more than others, which is to be expected. So here's what we're going to do. To make our experiment even more interesting and the behavior even clearer, let's increase the scale. Instead of drawing numbers from 0 to 19, let's draw numbers from 0 to 1,000. In other words, 1,001 bars. Here we go. Okay, as expected, the straight line continues, and so does the fluctuation. No surprises there. But now the fun begins. Instead of drawing a number and going to the bar to increase its size, we're going to draw two numbers, add them up, and go to the result bar. For example, if the number 50 and the number 25 come up, we go to the 75 bar and increase its size. But there's a small problem. It can happen, and it will happen, that the largest number comes up twice. In this case, it would be 1,000 and 1,000. Then the sum would be 2,000, and we don't have 2,000 bars. So I'm going to increase the number of bars to 2,000, just to cover all the possible sums. Now let's draw lots. Look at that. The question now is, why did you make a triangle? And the answer is very simple. Check it out. How many possible ways can this add up to 0? Only one, right? 0 plus 0. And to give one, it can be 0 plus 1 or 1 plus 0. And to make 2, it can be 0 plus 2, 2 plus 0, or 1 plus 1. In other words, the bigger the number, the greater the number of combinations that result in it. Even when you write it on the screen, it forms a triangle. Then it increases until it reaches the number 1,000, which is the number with the most combinations. Then it decreases until it reaches 2,000, which is as rare as 0. The greater the number of combinations, the greater the chance of this sum happening, and the bigger the bar will get. And you think that's crazy enough? My friend, let's move on. Let's repeat the same process. But now, instead of drawing and adding 2 numbers, let's do it with 3 numbers. And bro, get ready, because now it's too beautiful. This shape that has appeared is called a normal or Gaussian distribution. And this distribution is very, very important in mathematics because of the large number of natural phenomena it can model. And the fact that it appeared when we added up the random numbers is explained by the Central Limit Theorem. The Central Limit Theorem says that absolutely everything. Now, instead of adding up 3 random numbers, we're going to add up 100 random numbers just to intensify the effect even more. The more random numbers we add up, the more concentrated the distribution becomes in the middle of the interval. Just look at 0. It never left. That makes perfect sense. What is the chance that we draw 100 random numbers and all 100 come up with 0, so that the sum can come up with 0? It's very, very low. It's a very specific situation. The more random numbers you add up, the more concentrated the distribution becomes. The more concentrated it is, the more predictable it becomes. And the more predictable, the less random. Conclusion, option B. Adding random numbers decreases randomness. And what we're seeing has nothing to do with the fact that they are pseudo-random numbers. This behavior is a consequence of mathematics itself. In fact, it's just the opposite. The more truly random the numbers are, the more perfect this behavior will be. And bro, if we keep increasing the amount of random numbers being added up, the distribution becomes so concentrated around the average, but so concentrated that it meets determinism. Look at that. If you add up 10 million random numbers, the chance of them falling close to the average is so high that this happens. Practically a single straight line around it. That's fantastic, bro. And it's very curious to think about how the concept of randomness in the minds of human beings is strongly linked to the concept of equality. For example, imagine this situation. An uncle came to your house and said, "You're going to throw this dice twice. If you get 6 both times, this present I brought you is yours. If not, it belongs to your cousin." Knowing that the chance of you winning is 1 in 36, do you really think that this gift is being given at random? By definition, yes. If it has a 0.0001% chance, it's still random. But in practice, this uncle is quite a son of a... From that point of view, the lottery is also a random game, except that it contains very little randomness, since the outcome is fairly predictable. See you in a bit.